All right, now let's look at our reactions of enolates, and let's just dive right into unsymmetrical carbonyl compounds. Let's look at this molecule here. We've got a cyclohexane boring, a cyclohexanone, a double bond here. That's more interesting. And let's put a methyl right here. So if this is carbon 1, of course, 2-methyl cyclohexanone. Note here's our carbonyl carbon, so here's an alpha carbon here that is tertiary, only has 1 hydrogen on it, and 3 R groups on it. Here's an alpha carbon here that is secondary, 2 R groups on it, 2 hydrogens. It's unsymmetrical, which means if we react it with a strong enough base, we could either pull off one of these 2 hydrogens over here to get this enolate anion, here's its resonance, or we could pull off this hydrogen over here to get this enolate anion, and here's its resonance form. What we note, tertiary versus secondary, tertiary is more sterically hindered. Secondary, less sterically hindered hydrogens, which means a base can more easily snag those 2 hydrogens, which means its activation energy of a base coming in here to get a hydrogen is lower. Lower activation energy means faster reaction, which means the reaction of a base to snag one of these 2 due to steric hindrance and activation energies is a faster reaction than coming in to snag this one. So this is our less hindered enolate. The reaction happens faster. We call that the kinetic enolate anion. Well, if a base comes in and snags this hydrogen on the tertiary carbon, we know it's going to go slower, but check this out. Look at this double bond here compared to this double bond here. Can we see that this double bond is more stable? This has a hydrogen on here. There's no hydrogens on this double bond. This double bond down here is more substituted. More substituted double bonds means greater stability. Therefore, this is a more stable enolate than this one is. So although the reaction happens more slowly, it gets us a more stable enolate anion. That's our thermodynamic enolate. And right now you should be getting some deja vu from the beginning of the semester when we were looking at kinetic versus thermodynamic products with dienes. All right, so good news is we can control how these reactions are going to occur. What if we want the kinetic enolate? What conditions do we put our reaction under to make sure we get the fast reaction and we don't get the more stable product? Well, we need a strong non-nucleophilic base such as LDA. Recall when we looked at LDA, it's a very strong base, pKa of 40. It had the 2 isopropyl groups on there, which means it's sterically hindered. So if we have a sterically hindered base, it's not going to want to try to get this hydrogen in here. That hydrogen's protected by being tertiary carbon. This hydrogen's being protected more. These 2 are more available to be snagged, less sterically hindered. So a strong sterically hindered base like LDA is going to snag a less hindered hydrogen. Polar aprotic solvents are the way to go. All right. So our main solvent for the kinetic product is THF. And the other thing to remember, this is the fast reaction. It has the lower activation energy. This reaction has the higher activation energy. So if you lower the temperature, there might not be enough energy to overcome the activation energy barrier to get the thermodynamic product because it's the slower one. So with that lower temperatures, you're going to favor the lower activation energy, the kinetic product. Normally we run this at minus 78 degrees. And if you look at minus 78 degrees, you might be thinking, that's awfully specific. What's the matter with minus 80? Whatever happened to minus 75? Why minus 78? The deal is we want to run it at a constant temperature, and it's tough to maintain a constant temperature at low temperatures unless you have something that will freeze or melt at that certain temperature. For example, if you want to run a reaction at 0 degrees Celsius, you run our reaction in an ice bath because water and ice, water freezes at 0, water melts at 0. As long as you have ice and water mixed together, you know the temperature is 0. And you don't have to monitor the temperature. Is there ice there? Yes. Is there water in there? Yes. It's at 0. Minus 78 is chosen because that just happens to, we have a mixture of things that we can get very readily that has that as the point. If you mix dry ice and acetone together, that mixture will be at minus 78 degrees Celsius. If we were in the lab, usually we have a little dry ice around left over from the Grignard reaction, and we actually make the dry ice acetone bath very, very cold. Minus 78 degrees Celsius for that thing. You put it in a beaker, you put it on the lab bench, and after a couple minutes, the beaker is frozen to the lab bench due to just water that happens to be around on the outside of the glass. All right, but these low temperatures, the dry ice acetone bath that you'd run it in, favor the kinetic enolate. Well, what conditions favor the thermodynamic enolate? Well, it needs a strong base, but we need equilibrium conditions. Note, if you want the equilibrium, the thermodynamic product is the one that you get more of at equilibrium. You need equilibrium conditions, which means you need a base, and they're not that strong, such as ethoxide or tert butoxide. These alkoxides, note, excuse me, note the overall reaction doesn't seem to lie to the right very much, but the product you're going to get will be the thermodynamic product because we've put it under equilibrium conditions. So you use sodium ethoxide, potassium tert butoxide as your strong base. You want a protic solvent, an alcohol. So hey, if you're using sodium ethoxide as your base, use ethanol as your solvent. If you're using potassium tert butoxide as your base, use tert butanol as your solvent. And since these reactions, the thermodynamic, are slower, they have the higher activation energy. You need enough energy in your reaction to overcome that activation energy, so you run at a room temperature about 25 degrees Celsius. All right. Which means, check this out, if you have this reactant right here, okay, we've got a carbonyl, it's a ketone here. Note it's not symmetrical. At the alpha carbon, these guys down here don't matter. We say, okay, if I add this base here, an alkoxide in methanol or in ethanol at 25, okay, those are our thermodynamic conditions. That means we're going to make the negative charge here. We're going to snag the hydrogen that's attached to the right alpha carbon, the more sterically hindered one. If we would have run this reaction with LDA, THF, minus 78, we would have made this one under here. Would have made the negative, put the negative charge over here, remove one of these hydrogens. And here we go. We take this guy right here to pentanone, and at LDA, THF, minus 78, this is the less sterically hindered carbon. These hydrogens are easier to get to. So LDA is sterically hindered base. We're going to make this enolate anion right there. Now this is going to lead us to a bit of a problem with stereochemistry. Say you had this molecule right here. You've got this phenyl ring, the carbonyl, an alpha target carbonyl. You had a hydrogen, a methyl group, and an ethyl group. Note that this carbon now is chiral. And you only had this one enantiomer here. You only had this guy. You went through great pains to make sure you only had this enantiomer. And so you want to run a reaction with this molecule, and who knows what reaction you want to run, but you're like, okay, I want to run this certain reaction. I need it under basic conditions. And instead of adding the other reactant, the first thing you did was put it under basic conditions, put a little OH minus in there and water. That's going to be a problem, because recall that we are under thermodynamic conditions here. This OH minus, now the reaction does lie to the left, but this OH minus is going to snag this hydrogen, the sterically hindered hydrogen right here, and make this carbanion. And recall that the geometry of a carbanion is trigonal planar. The lone pair here is in the unhybridized p orbital, so this is a trigonal planar carbon now, And so this is an equilibrium. The base will come in, it'll snag that guy, but equilibrium says we're going to go back to form this thing right here, except if this is a trigonal planar carbon, from which side will this hydrogen come back in on in the reverse reaction? Well, it's trigonal planar. The hydrogen can come back in from either side. So if you just added that base, went away for lunch, you're going to find out when you came back you actually had a 50-50 mixture of these two reactants here. You spent a whole lot of time just trying to separate this one enantiomer from the other one. You threw in some base, weren't thinking about it, and now you're back to where you started, racemic mixture. So we have this alpha carbon racemization. When you're in the lab, it's something to consider. You have to be extremely careful the order in which you add reagents when you're dealing with chiral alpha carbons, because if there's base or acid around, mainly base here to pull this off, you're going to get some bad things, racemic mixtures, nastiness. Well, that's bad. Now that we have this knowledge, the question is, do we want to use our knowledge for good or for evil? Well, let's use it for good, shall we? Let's look at halogenation of that alpha carbon. Here's a reaction we can do. If we've got a ketone here and the alpha carbon has a hydrogen on it, turns out if we just reacted with a halogen, X2, in acid or basic conditions, note we need the acid or the base for the tautomerization catalysis. But if we have that, acid or base, to catalyze the tautomerization, we add X2, you're going to put X. You're going to put a halogen on that alpha carbon. So if you add cyclohexanone, just throw in some Cl2 and HCl and H2O, you're going to put 1 chlorine alpha to that carbonyl carbon. All right. And the best way to do it if you're doing an acid is often use acetic acid as our catalyst and as the solvent. So if here we have acetone here, CH3, C double bond O, CH3. If we use Br2 and acetic acid, we know, okay, ketone, Br2, acetic in acid, we are going to put a bromine alpha, so we're going to end up with a bromine there. Mechanism, you've might be able to figure it out. Let's go through it. First thing is acid catalyzed tautomerization. The oxygen attacks that hydrogen, protonates it. We get the tautomerization to this enol here. Then this carbon, this carbon will attack this bromine here. We can write it this way, where the double bond reforms and between the oxygen and the carbon, and the carbon-carbon double bond breaks and attacks the bromine. We can write it that way. And the bromide comes in, takes that hydrogen. The horrible fact of the matter is I'm not going to worry too much about the mechanism for these. Mainly I want you to know that a ketone and Br2 with acid is going to put the bromine alpha. Alright, that's nice. But something interesting happens when we have it in base. If we do a base catalyzed reaction, no, we would expect the same product. If we have this carbonyl compound here, we've got 2 hydrogens alpha to that carbonyl, Br2 now in base. We'd expect to put a bromine on there. The problem is it's very difficult to stop at 1 addition of bromine under basic conditions. The fact of the matter is you're going to end up putting 2 bromines on there. Fact is, however many hydrogens you have alpha to that carbonyl, that's how many bromines you're going to put on there. When we look at the mechanism, we see that OH minus is going to take this hydrogen and make this carbanion, which reacts with the Br2 to put that bromine on there. However, we're under basic conditions. Base, a nice and strong base here, is going to probably want to take this hydrogen next, and it will, and then make this enolate anion here, and the bromine will add to, the next bromine will come in and add to that same alpha carbon. Which means, man, what if you had like a crazy unsymmetrical thing. What if you had hydrogens on the other side? Well, you would get bromines on the other side. And someone said, well, that's nice. That reaction seems to be less useful because you can't just put one bromine on there. You'll end up taking every alpha hydrogen off and putting a bromine on there instead. How useful is that? And someone said, well, I think I'll find that extremely useful. Let's use my knowledge for good. And along comes the haloform reaction. Don't ask me why. Everyone loves a haloform reaction. It's kind of cool, but I see haloform reaction on lots and lots of organic exams. So I've never run it, but some people must get really jazzed by it. So let's look at it here. Haloform reaction. Take R, C, double bond, O, CH3. Now our R group is going to be special. There are going to be no hydrogens on the alpha carbon of this R group. Whatever this R group is right here, there's no hydrogens on the carbon bonded to the carbonyl carbon. And you must start with a CH3, a methyl, on the other side of the carbonyl. If you had a whole bunch of halogen X2 under basic conditions, you're going to end up with a carboxylate and HCX3. Let's look at this. If this was chlorine here, that would be HCCl3 chloroform. If this was bromine, this would be bromoform. That's why we call it the haloform reaction. It's a really nice way of making chloroform. All right. Let's look at the mechanism here because there's some interesting points to it. We start with RC double bond O and these three hydrogens on the methyl group. Recall, you have to start with a methyl on this side. OH minus takes that hydrogen to make this carbanion enolate, which will attack, okay, we're adding iodine here, which will attack this iodide, and you put an iodide on there plus I minus. Do the same thing, then start with this guy here, add OH minus takes the next one, puts an iodine here, more OH minus takes this guy, puts iodine here, we end up with R, C double bond O, Ci3. But remember, hydroxide is the catalyst. We get it back. There's still hydroxide around here. And once we have this situation, it turns out Ci3 or CCl3 or CBr3 is a good leaving group. We have now changed this from a ketone into an RCOZ compound. And so hydroxide will attack the carbonyl carbon. That bond will break as it always does. The double bond reforms, kicks off that good leaving group. Now, interestingly, as we can see, we'll end up with once this leaving group is gone, we end up with the carbonyl here and the OH right here. That's carboxylic acid. And this is a leaving group's a fairly decent base. It's just going to come right back and take that hydrogen. Yeah, that hydrogen was from the OH minus catalyst for the tautomerization. That hydrogen is now this hydrogen, which is this hydrogen, which gets snagged by the Ci3 minus, and we end up with HCI3 iodoform plus our carboxylate. All right. Now, question, what if we ran this haloform reaction, but instead of OH minus as our catalyst, we used OD minus instead of a hydrogen with no neutrons in the nucleus? What if we used a deuterium with 1 proton, 1 neutron in the nucleus? What would our final product be? Yeah, our final product would be DCI3, or arranging things in and using chlorine, CdCl3, our main NMR solvent. So this is one way to make your NMR solvent deuterochloroform, is do the haloform reaction, but use deuterium instead of hydrogen in your catalyst.